Recorder is on, so you now need to keep all your evil comments to yourself. And looking at the chat, nothing important for me right there. Next thing is to share my screen. Screen sharing. Close my YouTube studio, disable calendar. All right, so I have the portion of the syllabus that's important, which is right here for those of you that are worried about the exam. The topic for today is A/B testing and actually a segue into interval estimates. So we're going to look at the confidence interval concept and bootstrap today, even though it's labeled as Thursday's lesson. A/B testing is a natural extension of the hypothesis testing we've been doing the last 2 lessons, and you'll get a nice example of that again today in the laboratory. So is that as clear as mud? Excellent. Let me go to the actual lesson. Got to get my counting right. Yeah, this is the right one. So A/B testing and confidence intervals. So I'm going to drone on for about an hour, and this is a good time to put a cardboard object up in front of your camera so it looks like you're here. And we will have the best trained cardboard cutouts. So A/B testing and confidence intervals are related in some sense. A/B testing is a procedure to systematically decide if 2 data collections are similar or substantially different and quantify the probability of that sameness or differences. So let's recall in your medium-term memory, we had four sets. We had set 1, set 1s, set 2, and set 2s. Do you remember those names? I need some.
Yes.
Okay, I got a few yeses. Excellent. When we plotted histograms of set 1 and set 1s, who can verbally describe what the histograms look like?
They were normal.
Normal, as opposed to abnormal.
I think one of them was relatively uniform, like straight across, and it was blue, but I don't know what set that was.
Okay, well, thank you for at least recognizing that there were colors. What were the colors of set 1 and set 1s?
Maybe like blue, yellow, red.
Blue and orange.
No, I'm thinking back to the blue and green versions. That would have been 2 lessons ago. So we had the blue-green ones, and on a number line where the left side is a 0 and the right side is in the thousands, where did the blue and green blob histograms plot? Were they closer to the 0 end or closer to the 500 end? Ah, now your memory's stuck. I knew I'd get you. It's not hard. You make it easy. Closer to the left or closer to the right of the picture?
Left.
Left. Okay, excellent. Now set 2 and set 2s, what did their histograms look like?
Closer to the right.
Closer to the right. Were they tall and skinny or short and fat compared to 1 and 1s?
Set 2 was short and wide.
Excellent.
And set 1 was tall and skinny.
Good. And then we looked at ways to answer the question, do they appear to be the same or do they appear to be different? We did it visually. I mean, you can look at it and tell, or we can apply a selection of hypothesis tests to tell if they're the same or different and quantify the probability of the difference. Or if we rename the sets from set 1 and set 1s, set 2 and set 2s, and grouped them. So we take 1 and 1s, put them together. That's one set. And we call it A. And then we take the short and fat ones, set 2 and set 2s. We group them into a single set and we call it B. That is the essence of A/B testing. So there's a whole book, a whole chapter in our textbook on the secret of A/B testing. And it's really nothing more than deciding whether two samples come from the same underlying distribution or not. Remember the tools that Farang showed you on how to assess whether a sample appears to be from a particular distribution that we find quite ordinary or not?
Is it the describe function?
No,
That
it was
tells us about the actual sample, but you're on the right track. So keep
was it
guessing.
like Shapiro Wilkes or Shapiro?
Very good, excellent. So you guys' short-term memory isn't bad at all. You're just using selective memory, just like I use selective hearing. So we've already explored tests to see if a sample has properties of normality, and we've actually explored tests that would let us tell if two samples appear to come from the same underlying distribution. Now, if they come from the same underlying distribution, there's an implication there, and the implication being not only did they come from a normal distribution, but they came from a normal distribution that has a particular population mean and a particular population variance. And since we're not always in God mode, we may not know what those population mean and population variances are. And so we have to what's the fancy word for flat out guessing?
Hypothesis?
No,
Inference?
keep guessing. We have to estimate.
Estimating.
Good. Brandon got it. Okay, excellent. So the computational thinking concepts we will be touching on today, or it's always going on in the background, is abstraction and pattern recognition. The other three are as important, but largely these two. And we're going to leave A/B testing details for your lab today, because there's two pretty good examples there already, and there's nothing new for me to introduce. We construct the groups, call one of them A, one of them B, and then we apply various hypothesis tests to determine whether they're the same or different. Instead, what I'm going to talk about is moving on towards interval estimates. And I've taken a lot of the content from a book from the United States Geological Survey, which is coming up on the guitar any minute now. Wow, it's taking forever to download. And it's this book, Statistical Method in Water Resources. So if all of this numbers and functions is halfway interesting to you and you're really lucky, you can get a job wading in freezing cold water making flow measurements. I want to see if I know the people in the photograph. I don't know either of them. But I know that if it's Jackson Lake Dam, that's really cold water. And this has a whole world of statistical applications in water resources data. These would all be valid for other areas of engineering. And this particular book is targeted using the programming environment called R. R, just like pirates say R, because R is the preferred programming language of pirates everywhere. We're stuck with Python, which is the preferred programming language of Voldemort and Harry. So let's get into the concept of interval estimates. In our descriptive statistics, we we presented a few common descriptive statistics that are used to decide or describe key attributes of a collection of data. One of those is the sample estimate of mean, the ordinary arithmetic mean. The other one is the sample estimate of variance. Lowercase s squared is written here. What are some of the other descriptive statistics that we can extract from a sample that you remember? So I got arithmetic mean, I got variance.
Okay, mu and sigma.
Mu is a population mean, sigma is a population standard deviation. So technically we cannot get those from a sample.
Are skew and kurtosis those?
Skew and kurtosis, excellent. Those are other measures of a sample, and they also exist for the population. You're on the right track. Let's get back to means. What kinds of mean are there? I mean, there's downright biblical mean, and then there's arithmetic mean.
Harmonic geometry.
Yeah, there was a harmonic mean, which is if you're going to be making music on the streets, and there was another one. I think Jackson, you said it. You said harmonic geometry. I heard that as harmonic geometry. Yeah, harmonic mean and geometric mean. Excellent, excellent. So there are various descriptive statistics of a data set that we can extract from the data set. And there's more than just the ones that we've listed, but those are the ones of usual importance. And these particular descriptive statistics are, by definition, they are estimates of the unknown population parameters. And in the population parameter world, we switch to Greek letters of the alphabet because they're hard to draw. So mu is the population mean. X bar is the sample mean. Sigma squared is the population variance. S squared is the sample variance. I forget what the symbol for population skew is, and so forth. And keeping this in mind, we can use our hypothesis testing ideas as a way to not only estimate a population mean, for instance. So how would you estimate the population mean at this point? I give you a sample of 50 things, and I ask you, what's the mean of the population these 50 things came from? Best estimate, how would you do it?
Would you get the sample mean? And
Good,
then,
correct. You use the sample mean as the estimate. And that's it, that's one number. And you've said the population estimate is 50.267. How comfortable would you be betting my life on that?
On a sample of 50, your life? Not very comfortable.
Well, thank you. You were so kind. How comfortable would you be betting your own life on that?
Not a
20%.
chance.
Even more uncomfortable. You might be tempted to say, I wish I had a way to tell you that the population mean is 50.25 plus or minus 10. So it could be 40.25, it could be 60.25. It has a 95% likelihood that it's somewhere between those two ranges. And that is the idea of an interval estimate. And we construct an interval estimate using tools we already have. It's used as an alternative to reporting a single estimate. And we'll look at the utility of reporting a range of values shortly. There are both parametric and non-parametric interval estimates. And these intervals can be used in some sense to test whether the population parameter is significantly different from some prescribed value, or B, whether the population parameter of two samples are significantly different from each other. And there's other things that we can do, but those are the big ones. So let's go first for a definition of an interval estimate. We'll focus primarily on means, medians, and measures of variability. So recall that we had a critter called a sample median. Who remembers in words what the sample median was?
The number in the middle?
Not bad. That's a good start. The number in the middle of what?
It's the 50th percentile.
The 50th percentile of what?
Of the sample.
So if I have a sample that contains 50 things, and the smallest thing is a 20, and the biggest thing is a 70, and 25 of the 50 things are smaller than 30, and 25 of the things are bigger than 32, what would be your estimate of the median?
31.
Good enough. So the middle, the 50 percentile, it's the number at which half the observations in the sample lie above that number and half lie below that number. And there's a prescribed algorithm to actually select the particular number. We taught you using the describe function, and it reports a 50th percentile. And that 50th percentile that it reports just so happens to be the median of the sample. So what is the median estimating? Is it a measure of how far to the left or right things are, or how spread out something is, or?
The median, it's the number exactly in the middle of your list, organized in order.
So it's called, to put different words into your mouth, it's a measure of central tendency. It's where the distribution is anticipated to center itself. So if I had a collection of 100 objects and their median was 10, and I had another collection of 100 different objects and its median was 2000, if they had roughly the same range, the same distance between their biggest and smallest value, you would be fairly comfortable in stating that the second one has a central tendency far bigger than the first one, almost 100 times bigger. So that's what a median is telling us. That's what a mean value is telling us, the measures of central tendency of a population. If we calculate either of those two, we get something called a point estimate. It's estimating a single value of the behavior of that population. Alone, point estimates do not portray the reliability or lack of reliability of the estimates themselves. So now we'll go into an example. Let's suppose we have two data sets cleverly named X and Y. So it's a collection of chromosomes, and if we mix these things together, we're going to get males. Both have a sample mean of about 50 and the same number of observations. So here we're going to go ahead and create the example. I'm importing NumPy and pandas. I'm going to create an empty list called process 1, another empty list called process 2. In the list of process 1, I am going to put the numbers 1 to 100. So it's a collection 1 to 100. In the list named process 2, I'm going to put in the numbers 41 to 61. So the variable process 1 and the variable process 2 contain different things. And we can plot them if we want to. Let's go take a look at the contents of process 1 just after we build it. So here's where we're going to split the cell. Again, we're taking advantage of the notebook's ability to do stuff one little bit at a time. Hopefully I don't have any other code above it. So that worked. And let's Process NR1, numbers 1 through 100. Process 2 isn't going to be much more interesting, although it's not clearly as long. So the list named process 1 and the list named process 2 have different lengths. Suppress that output. Now what I'm going to do is I'm going to sample with replacement from each of these two populations, if we will. Process 1 contains the numbers, the integers 1 to 100. Process 2 contains the integers 41 to 61. And I'm going to go to process 1. I'm going to pull a number out. I'm going to look at the number, write it down, and then throw it back in the bucket, and then shake the bucket. Reach in, pull a number out, write it down. We'll look at the number, write it down, put it back in, shake the bucket. I'm going to do that 500 times. And those numbers I'm writing down are going to go on a piece of paper that I've labeled lowercase x. I'm going to take the same with a process 2 bucket. So I reach my hand in, pull a number out. It's going to be some number between 41 and 61. Write the number down, store it on a piece of paper called a y, put the number back in the bucket, shake the bucket, pull it out, write the number down, put it back in the bucket, shake the bucket, reach in, grab another number, write the number down, put it back in the bucket, shake in the bucket. I'll do that 500 times. So now the length of this list X, how many things are in it?
500.
Good. The length of Y, how many things are in it?
500.
Also,
500.
yeah, good. And we're going to put them into a data frame so we can use some pandas tools. So we're going to create a data frame called boxdf, and we're going to use the pandas subsystem, create the data frame, and then we're going to assign the list X to the boxdf data frame, and we're going to give it the label capital X, and we're going to assign the frame Y, assign the list Y to the data frame column capital Y, and then we'll run the describe function. So I do that, and it tells me that cap X has 500 things in it, cap Y has 500 things in it. So did they come from the same process or not?
What do you want process?
Did they come from the same process or not?
Oh, no, they didn't.
Yeah, we know they didn't, but go ahead and support that assertion based on the describe function. So each one has 500 things. That looks the same to me. The mean of the X is 47. The mean of Y is 50. That's awful darn close. So that looks the same to me. The standard deviations are quite a bit different. The minimum and maximum values are different. The 50th percentile of X is a little smaller than the 50th percentile of Y. So are they the same or different? And your conclusion is they're probably different. Let's go ahead and activate the histogram and take a look at them when we plot them. Trying to remember, I can't remember how to get them to be less gold. So there is our histogram of the two plots. We can't see the blue bars that are behind these orange bars, but they're probably roughly right in there. So in terms of measures of central tendency, does just a point estimate of central tendency tell us anything about how good that estimate is? So for so for variable X, the mean value is 50. For variable Y, the mean value is 50. That's all the information you have. Are these populations the same or different?
From that information, they look the same, but
Yeah, you don't have enough. We're not taking advantage of the data that we have. If instead I said that the mean value of population X is 50 plus or minus 30. So I have a 64% chance that the population mean lies between 20 and 80. And I have a 64% chance for Y that the population mean lies between, let's see, I'll do this in my head, 45 and 55. Now you have something to discuss. So in the first case, although the mean value is the same, because the standard deviation is so big, that interval estimate that I just stated the interval estimate without really telling you where it came from. The interval estimate for case Y is 20 to 80. So the population mean for case Y lies between 20 and 80. The population mean for I got those backwards. The population mean for case X lies between 20 and 80. The population mean for case Y lies between 45 and 55. If you put those two intervals next to each other, you would certainly conclude that our estimate of the value for Y, because it has much smaller interval range, we're more confident in that. And if it was a life-making decision on your life, not mine, because you guys would throw me under the bus even before it gets here. I don't even have a bus route here, and I could see you tying me to the street and getting good video. Oh, it smushed his head like a watermelon. All right, so here we have basically recreated this, and this stuff looks like that's an artifact. Yeah, so in words, we see that the Y data all cluster relatively tightly around 50, whereas the X data have more variability. That's by construction, because we were God and created these populations. The point estimate of 50 for data set X is consequently quite a bit less certain than the point estimate for data set Y because of that greater variability in the X data. So if we were to report only the point estimate of 50, that alone fails to give any hint of the difference, although graphically it's quite evident. And that's why on the TV news, when they get the official liars, they're called statisticians, they normally report statistical sounding like stuff when they talk about a margin of error of plus or minus 3%. They're trying to convey rapidly in TV news, because plus or minus 3% doesn't sell soap. So they got to get away from that, get to the commercials real quick. They're trying to convey a picture just like this. So if they say Jojo Rabbit is likely to win the midterm elections because the polls indicate that he has 90% likability in the polls, plus or minus 3%. That's telling us that the mean estimate of the turnout for Jojo Rabbit is 90% of the voters, but it could be as high as 93 or could be as low as 87. And normally in that kind of stuff, they would be using an alpha value of 5%. So you notice I said alpha value of 5%, you all didn't even bat an eye. Abby is taking a nap, in fact. That's because the ideas of interval estimates and hypothesis testing are intimately related to one another.
So interval estimate is basically like z-square?
If we are using parametric, if we have decided that the underlying distribution is represented by a normal distribution, then we could use z-scores. But it is somewhat distribution dependent.
Thank you.
This sounds a whole lot like confidence intervals. That's what we're talking about, right?
It's the same thing.
Okay, just making sure.
But I'm taking the word confidence out because no one should have any confidence in a confidence interval. They're not confident, they're just interval estimates.
I see, okay.
So let's look at our variables X and our samples, cap X and cap Y some more. Given that the last couple class meetings, we've been hypothesis testing the crap out of things, let's go ahead and hypothesis test the crap out of these. So the first question I want to ask is, do the samples themselves appear to be approximately normal? Why do I want to ask that test other than it's right here in the notebook?
To know if we can use parametric tests.
That's correct. I'd like to use parametric hypothesis tests if I can, because they are known to be more powerful, and power gives me the ability to not only control my alpha error, but also my beta error. So we will apply our Shapiro-Wilk normality test because we've seen it before, and rather than worry about it, we'll apply it no brains required, and we're going to apply it at an alpha level of 5%. And so what that means is the null hypothesis is if indeed these data are normally distributed, then then we're assessing the chance that that normal distribution, ironically parameterized by these particular data's mean and variance, produce the observed result. And we have emitted a type 1 error of 5%. So we have a 5% chance of rejecting our null hypothesis when in fact it's correct. And so we run it and it tells us that our attained p-value is very small, pretty close to 0. And our conclusion is these data are probably not Gaussian. And we kind of could have deduced that simply by looking at the plot of the distribution. Because if it were Gaussian, what would we expect the blue bars to look like?
Bell shape.
Would
Yeah.
look like
Be kind of some kind of either at least triangular or a bell shape. Similarly, we can play the same game with Y, and we're going to get the same result. And again, the graphic is also telling us the same story. This looks kind of just like a vertical bar, almost a uniform distribution. In fact, it is a uniform distribution. No triangular or bell-shaped behavior at all. And when we test that, we come up with the conclusion that neither of those are bell-shaped. We can apply a Mann-Whitney test, which is a non-parametric test. So it does not care what the underlying distributions are, and we can test if the mean values of the two distributions are the same. So that's what Mann-Whitney test is going to do. It's going to take the mean of X and the mean of Y, actually subtracts one from the other, and then it takes those resulting differences and determines if those differences are explainable by chance or not. So I think the printed logic doesn't make sense. Let me just change this.
So basically, it's determining where the means are statistically different enough for it to be a different distribution.
That's the idea. Let's go ahead and run this, and we'll go back and we will jack with the actual contents of the distribution and rerun this, and we can show that both graphically and in the test. So the result here is the mean value is probably the same, which is not a surprise. Let's go ahead and modify, see which one's easier to mess with. So I'm going to rerun that. Now I've taken the mean value of y and made it 150. When we plot them, clearly the blue and the orange don't even plot in the same place. So this is a no brains required interpretation. Those are two different, those data come from two different processes, which we know ahead of time. Those words are no longer correct. We still get probably not Gaussian, probably not Gaussian. And now I expect it to tell us that the mean values are not the same. Sure enough, probably different means. So our tests, more or less in this case, confirm what we can see by plotting. But if the differences aren't quite as obvious, so let's just shift this by a value of 20. So 61 to 81. That's going to be different means, different processes. So all we did was monkey this to the right a little bit. So that is still a different mean. And depending on this p-value, that actually unintentionally helps control how far to the right we can shift something. So if we go just a value of 10, we still have a different mean. The p-value rejection is pretty small. And if we finally get back to, let's go to the meaning of life, 42 to 62, because that's what deep thought spent several million years. The answer is 42. You didn't ask the right question. And so shifting from 41 to 42, we're still at the same mean. Okay, so let's just continue on with the story. So at this point,
Excuse me, Professor.
yes?
Okay, I have a quick question. The middle value that we were changing, how do we call that? Is that the increment or
How do we call what?
the middle value that we kept on changing earlier in order to get different graphs?
Oh, I was just changing the range of the population.
Yeah, I understand. But okay, what was that middle value? Is that the increment or what? No?
Well, I made a population from 1 to 100 and from
Okay.
41 to 61, and I was just changing
Okay.
the population limits.
Okay, I got it.
It wasn't magic. I wasn't trying to do magic. I've got other ways to confuse you than that. So continuing on with the story, at this point, what we really know is that the mean values are about the same in these two samples. But we also know that the two data sets are not alike. And if we were not stupid, we would see, well, it has to do with the variance. As an alternative to just reporting point estimates, interval estimates are intervals that have a stated probability of containing the true but unknown population value. In our example, the mean of cap y is 50, and we're pretty sure of that because the sample variance is small. Sample variance and sample standard deviation are related to one another through the mighty square root function. The standard deviation is the square root of the variance. So when I say variance, a lot of times you can substitute the word standard deviation in your head. So the mean for cap y is 50, and we're pretty sure of that because the sample variance is small. If our sample had also tested out as normal, we could have stated that the estimate of the population mean is 50 plus or minus 18, where 18 is 3 standard deviations, and that would occur with a probability of 99%. So right here, that statement is called an interval estimate. Now we didn't do that because our data didn't test out as normal, although there are other things we can say about it when it's not normal. So to reiterate, if we were to write that the estimate of the population mean for category cap Y is 50 plus or minus 18 with a probability of 99%. Our interval estimate would be, let's see, 50 minus 18 would be the 99% interval that contains the true but unknown population mean is 32 to 68. And that statement is an interval estimate. They're stated either as the interval or, as we've stated here, 50 plus or minus 18. In general practice, we usually present two-sided intervals where the probability of the true value being higher than the upper limit is assumed to be equal to the probability of the true value being lower than the lower limit. There are also one-sided intervals. Intervals are wider for data sets that have greater variability in the same number of data points. So in our case of X and Y, because X has that's a strange siren going off in the background.
Okay, I thought I was the only one hearing that.
Yeah, they're just testing it. That's it.
And that's from campus.
Okay, I don't hear those kind of sirens very often in this country. It was common when I was overseas as a young man playing Army, but that was for a whole different reason. So in the above example, the interval between 38 and 62 would have a 95% probability of containing the unknown true population mean of data set Y. That's data set Y. It would take a much greater interval, say between -6 and 106, to have the same probability of containing the true mean of data set X. And notice the interval in those high variability cases, because we have the God mode, we actually created the process that generated the data. We have an interval that's actually bigger than the contents of the population. That's unusual and is an artifact of this particular example. So the difference in the reliability of the two estimates is therefore clearly stated using interval estimates. Interval estimates provide two vital pieces of information that point estimates themselves cannot. First, they provide a statement of the probability or likelihood that the interval contains the true population value. So that's a measure of reliability. They also provide a statement of the likelihood that a single data point with a specified magnitude comes from the population under study. Interval estimates for the first purpose. So if a purpose of our interval estimate is to make that statement, those interval estimates are called, okay, Cade, you can talk now.
I'm sorry, could you say it again?
If we're producing interval estimates, in order to produce a statement of probability or likelihood that an interval contains the true population value, those estimates are called?
We call those confidence intervals.
Excellent. If, on the other hand, we're making the interval estimate to state the probability that a data point with particular magnitude comes from the population under study, that type of estimate is called a prediction interval. Both are used quite a bit in the world of prediction engines and regression modeling and stuff that's coming up in your near future. Although they're quite related, the two estimates are not identical, and should not. There, that works better. It's terrible when you have to mess with your English live. Although they're related, they shouldn't be interchanged. So a confidence interval is a particular type of interval estimate, and a prediction interval, although related, is a different type of interval estimate. And they're both in common use, and they have their appropriate places. And I will be somewhat trite and say that that will normally be obvious by context. So let's look at some things that are relevant for interval estimates. We're actually going to run through an example. But first, let's visit our textbook. You know the textbook, inferentialthinking.com.
Oh yeah, I read that thing a lot.
Yeah, I thought so. How many people have been there today?
Oh, I spent my
Everybody, because we're here right now. So I'm taking from the chapter on estimation the idea of percentiles. We've talked about this. In fact, Wiley opened the class with a question on Weibull plotting position, which is a formula that gives us a way to empirically estimate percentiles. So if we sort data in increasing or decreasing order, then that sorted data has what's called a rank order, not odor, rank order. Thinking about ranching here. And the percentile is the value at a particular rank. For example, if your score on a test is the 95th percentile, a common interpretation is that only 5% of the scores were higher than yours. The median is 50th percentile. It's commonly assumed that 50% of the values in the data set are above the median, 50% below. But there's a bit of care required in giving percentiles the precise definition that works for all ranks and all lists. And the book goes on to explain why we have to be somewhat careful if we were writing our own scripting to calculate percentiles. So,
You know, it's the beginning of Ramadan next week, right?
I don't even know what that is.
Joking. It's actually next month on the 13th. Oh, no, I was on. Yeah, never mind.
oh, thank you. I forgot what I was talking about. To see why, let's consider an example where all the students in the class score a 75 on a test. So if there was a test that had 75 points and everybody scored 75, normally everyone would go, woohoo, that's great. But the person that's going to have to choose letters of the alphabet to put next to your name to decide your future on whether you go work for Amazon or Walmart has to decide what that 75 means. So if everybody in the class got a 75, the 75 is a natural candidate for the median, but it's no longer true that half the scores are above or below 75. 75 is also a natural candidate for the 95th percentile or the 25th or any other percentile. Ties, that is equal data values, have to be taken into account when defining percentiles. So in our case, it's not going to be a big deal because we're going to use a built-in function that does it. You also need to be somewhat cognizant of how far up the list to go when the relevant index isn't obvious. For example, what should be the 87th percentile of a collection of 10 values? The 8th value or the 9th value or somewhere in between. In general, what algorithms do is they linearly interpolate somewhere in between to get these particular percentiles. Now, if you have 100 items that are sortable, the 87th is quite trivial to find. The 87th percentile is estimated by using the value associated with the blank value in the sorted list. Somebody fill in the blank. Short-term memory is all gone, huh?
Because wouldn't we be taking the percentile out of the space or amount we have?
Well, if we had 100 items and I want to know what the 87th percentile is, describe how to estimate the value of the 87th percentile.
It would be the value which has 86 or 87 of the data below it.
Okay, close enough, yeah. You had 100 items, you sort them. Let's go big, small to big, and then we take the 87th item off that sorted list, and that would be a pretty good candidate for the 87th percentile. So numerical data can be sorted in increasing or decreasing order. We've seen that already. The value of a numerical data set has a rank order, and the percentile is the value at a particular rank. And we exploited this in our plotting position formulas. So Grin, Gorton, Cunnane, Weibel, California, Hazen, and all those other, I think there was Turk formula. I can't remember all the names. There are a bunch of them. Everybody that has a name that figured a way to get a plotting position formula published has a formula named after them. We've exploited the feature in those formulas to a great deal, is taking the rank order and associating that with a percentile definition. So for example, if your score on a test is in the 95th percentile, we interpret that as 5% higher and so forth. This looks verbatim from the textbook, so I'm not going to read it to you again. But let's look at the last part. What should be the 87th percentile of 10 things? The 8th value, the 9th, or somewhere between. Again, we already addressed this issue with our plotting position formulas earlier. So our plotting position formulas really takes care of a lot of chapter 13 for us, no brains required. Let's go with a numerical example. So before giving the general definition for all percentiles, we'll define the 80th percentile of a collection of values to be the smallest value in the collection that is at least as large as 80% of all the values. And we're going to use an absurd example to illustrate some of the challenges. So for example, let's consider the sizes of the 5 largest continents: Africa, Antarctica, Asia, North America, and South America are rounded to the nearest million square miles. And we're going to use the data science subsystem, which just is another module that has function names that are a little bit more humanly readable. So in the data science module, the make array pretty much uses the NumPy subsystem. Okay, so we've imported it. Now we have the sizes of our continents: Africa, Antarctica, Asia, North America, South America. So our biggest continent is 17 million square miles. Our littlest continent is 6 million square miles. And what we want to know is what's the 80th percentile. Well, if we look at 80th percentile as the same as 4 parts in 5, so does that make sense? Yes, 1 part in 5 is 20%. So 4 parts in 5 would be 80%. That would mean it would be the 4th element out of the 5 things. So if we sorted it, we'd have 6, 7, 9, 12. There's our 4th element. So the 80th percentile is clearly 12 million square miles. And we can see that 80% of the values are less than or equal to it. So 12 is less than or equal to 12, 9 is less than or equal to 12, 7 is less than or equal to 12, 6 is less than or equal to 12, 17 is not less than or equal to 12. So 4 of the 5 elements of the list are less than or equal to our target value, so that target value is our 80th percentile. Now the 70th percentile is the smallest value in the collection that is at least as large as 70% of the elements of the sizes. Now 70% of 5 elements would be 3.5 elements. So the 70th percentile is the 4th element on the list. That is also 12, but we already know that that's the 80th percentile. So using just that definition for percentiles is not terribly useful. But wait, there's more. What we can do is, because it's 3.5 elements, we can apply a scheme that says that 12 is the 80th percentile, 9 is the 60th percentile, and somewhere between 9 and 12 should lie the 70th percentile, which is not contained in the list, but we can recover a numerical value to estimate the percentile. And that's called the percentile function. We've seen them as quantile functions in our presentation. So in the data 8 or the data science subsystem, they have a function called percentile. And to use the function, you tell it the percentile you want it to find, and you give it the list of the things to find it. And it returns a 12. If we go to 80, it also returns a 12. So their percentile function is not doing any interpolation, which is why we often fit data models to our plotting position formulas, because all we have is these percentiles from our data, but we also have the ability to pass a function through that data and then make inferences from the function. And that was the whole part of the data modeling. So let's generalize the definition. Let P be a number between 0 and 100, and the Pth percentile of a collection is the smallest value in the collection that is at least as large as P% of all the values, similar to what we've discussed above. By such a definition, any percentile between 0 and 100 can be computed for any collection of values. It's always an element of the collection. In practical terms, suppose there's n elements in the collection. To find the Pth percentile, do the following. Sort the collection in increasing order. Does that sound familiar?
Mm-hmm.
Yeah, that'd be a yes. Find the P percentile of n. P divided by 100 times n, call that k. If k is an integer, take the kth element of the sorted collection. If k is not an integer, round it up to the next integer, take that element of the sorted collection. So that almost sounds like a Weibull plotting position function. There's a reason it almost sounds like that, because it is. There is a set of databases called scores and sections, and it contains one row for each student in a class of 359 students. The columns are the students' discussion session and the midterm score. So I have a copy here locally, but if you want to get the file yourself, you could take this particular path. So here's scores by section. So section 1, section 2, section 3, section 4, 5, 6, and we have various scores. So you were asking what your scores were on the first midterm. They range between 0 and 24, although these are not your midterm. I'm just doing that to, again, regain your attention. So I'm going to copy the file to my local, oh, that actually worked. And now we're going to look at the contents of the file. So we're going to read the table. This is very much a pandas wrapper on top of the pandas subsystem. And we're going to read the file called scoresbysection.csv, and then we're going to print out the table, and it gives us the section and the midterm value. So let's make a histogram, again, using the tools from our textbook that everybody reads all the time, and see if we can approximate the 85th percentile just by looking at it. So here goes nothing. Hopefully the cool plots still work. Oh, thank heavens. So here is our histogram. And so the 50th percentile, if you think of this as a object made out of a thin metal that takes on this shape, the 50th percentile would be where that thing would balance. If you put something on it to make it balance. So the 85th percentile is going to be where 85% of it is to one side of the balance and the other 15% is to the other side. And so if we look at the 85th percentile or do percents per unit, I have 5% here, 10, these three add up to another 10, there's 20, 30, 40, 50. So the 85th percentile looks to me to be somewhere in here, maybe around 21 or 22. If we use our percentile function, we want it to return the value from the data set. The name of the data set is scores and sections, and we want to take the first column, excuse me, the second column, which is column 1 in Python. Column 0 would be the sections, and get the 85th percentile. And when we run that function, we recover a 22. So our eyeball value wasn't too bad. According to the percentile function, the 85th percentile was 22. To check that it's consistent with the definition, we can apply the definition directly. First, we'll put the scores in increasing orders. So we're going to sort the scores. Then we're going to compute the length of sorted scores. There's 359. And so next we want to find the 85th percentile of 359, which is 305.15. That's not an integer. But by definition, the 85th percentile is the 306th element of the sorted scores, which by the Python indexing convention is 305. We do that and we get the 22, which is the same answer. And we could get elaborate. We could make the result of this an integer and then sort directly on that, which is what the percentile function does. So in the future, if you have to, just use built-in percentile functions. Next idea are quartiles. You've seen these already. Farang showed you those, and they are a property that comes from Pandas data frame. Remember where we get the quartiles from? Those of you that are actually watching the TV and can read the pandas.dataframe sorted scores dot whatever that last word is, gives us the method that will produce our quartiles. Oh, your really short-term memory sucks today, guys. Describe, thank you, Harper. Good. So we're going to, let's use our percentile function first and recover the 25th, the 50th, and the 75th percentile. And we're using those three because that's what the describe function produces. And we get 11, 16, and 20. Now if we use our Pandas data frame describe function on the same object, sure enough, the 25th percentile is 11, the 50th is a 16, and the 75th is a 20. That's kind of cool in some sense. What if we wanted to know the 95th percentile? Our little describe function doesn't do that by default, but we can modify our percentile script, find out that the value of 24 corresponds to the 95th percentile for these particular data. And if we wanted to make decisions based on the 95th percentile, that's how to do it. So we're going to move on to bootstrapping. Let me check on time. I'm good on time. We're going to look at a black. God, I wish I knew why it did that. My screen just went black. A data scientist is using data in a random sample to estimate an unknown parameter. So stuff we've done. We've taken a sample, we've calculated a mean value, and we want to declare that that mean value estimates a population value. So we use a sample, calculate a statistic. Once we've calculated that observed value of the statistic, we could just present it as the estimate and go on about our merry way, and move on, hopefully get to lunch soon. But we know that that random sample is just one possible collection from the underlying population that we could have recovered. And so we know the estimate is one of a number of plausible estimates. So how much could those estimates vary? That kind of gets us back to this interval estimate case. If your job's on the line, you probably want to do more than just report, oh, the mean value is 53. I'm going to lunch. Because what if the mean value is in fact 52? So then you're wrong. And you know what happens at jobs when you're wrong? You either get promoted or fired. There is no middle ground. So the prudent person would come up with some way to estimate the uncertainty or estimate the reliability promoted customer. So to answer that, it would appear that we need to take another sample from the population and compute a new estimate based on the new sample. And that would be ideal. But it turns out we don't have the cash to go back to the population and throw money at it and draw another sample. So it looks as though, well, we're out of luck. But there's a technique called bootstrapping, which can help out. Because it's not feasible to generate new samples from the population, bootstrapping generates new random samples by resampling our original sample. So essentially what bootstrapping does, you're going to see this appearing in other contexts. Our original sample is now treated as if it were a complete population. It's a hack, but it's quite useful. So let me go back to the introductory part of the lesson. So process 1 and process 2 were my population. And then from process 1 and process 2, I sampled with replacement 500 times. So now my X value and my Y value represent samples of the population. In this particular case, those samples are larger than the entire population space. So if I wanted to resample, in this case, it makes a lot of sense to sample from those larger ones, because surely a population that has 100 things in it, if we sample replacement 500 or 5,000 or 10,000 times, it's pretty likely we're going to see at least one of the things, one of everything in the population more than once. Bootstrapping leverages on that somewhat obvious statement. So we're going to look at how much people get paid in the city of San Francisco. The numbers might surprise you because these are circa 2015, and they might make you want to move to San Francisco until you realize that you can't afford to live there at any price. So San Francisco Open Data is a website where the city and county of San Francisco make some of their data publicly available. One of the data sets is compensation data for employees of the city. These include medical professionals at city-run hospitals, police officers, firefighters, transportation workers, elected officials, tax collectors, and so on, and all other employees of the city. And the compensation data for calendar year 2015 is in this table. I'm just going to look at the table briefly. So it has year type, a particular year, organizational group code, job family code, what the job family is, the job code, the actual job description, an employee ID, that's like an employee number. And if you look at those numbers, city of San Francisco employs at least 53,000 people. That's an awful lot of people to run a city. And then the salaries are listed in this column: overtime, other salaries, total salaries, retirement, benefit, health and dental costs, other benefits, total benefits. Somewhere out here we get total compensation. So here's an employee. The first one is making $117,000 a year total compensation as a water quality technician 1. So Abby, if this engineering gig doesn't work out for you, that's pretty good scratch to go to San Francisco and scoop jars into a wastewater treatment plant, take a sniff and go, yep, that's poop. And then we'll write that down and then move on. And then let's see, what's another one? I was trying to find somewhere they have a carpenter. You would think the highest paid person in the city might be a doctor or a mayor, but it turns out it's a carpenter. There is a carpenter somewhere on this list that's compensated a whole lot more than anyone else. And so that's the person who really built the city of San Francisco. Okay, so it's a database. In my case, I can copy it from the local computer and I will print it. And so now it's returning the contents of the database. And look how big it is. So this is almost, it's probably got over 43,000 rows in it. So that's probably a wee bit on the big side to load this in Excel and then go find something in particular. This is where our computational thinking and data science is going to start to have value. You may have heard the terminology big data. 42,000 things is not big data. Make it 450 billion things, and then that gets the big data people all giggly and wiggly. So there's one row for each of the 42,000 employees. There's numerous columns of department affiliation and details. And here's the row that corresponds to the mayor, which in 2015 was Edward Lee. And so he is in general administration and finance. His department code is mayor. His department is mayor. He is in the elected officials union. Go figure, California would have one of those. And his job is mayor. And his total compensation, $379,000 per year. Of that, a fair amount was benefits other than salary. And the retirement didn't help him much since he ended up dead. So we're going to study the final column, total compensation. That's the employee's salary plus retirement and benefits plans. Financial packages in a calendar year can sometimes be hard to understand as they depend on the hiring date and whether the employee is changing jobs. So for example, of the lowest compensation, if we sort the database, it looks kind of strange because we have somebody that, how come it's not letting me scroll right? We have zeros that don't make a lot of sense. There we go. Trying to get more screen real estate. It is denying me. There. That's about the most screen real estate I can get. So there is still content off to the right. Where we have the sorted results. So now let's take the median of the total compensations. We already know how to calculate a median. We'll call it the population median is the 50th percentile of the total compensation column. And because the database represents the entire population, we call that a population median. And that changed value. It shouldn't do that. What did I change? Oh, I'm in the wrong place. There we go. Let's first segregate salaries above 10,000. So because San Francisco has a high minimum wage, anything less than 10,000 would have represented an incomplete year. So we go ahead and get the population less than 10,000. You'll notice that the database is running right now. Looks like Amazon has gone into slow mode. Hate it when that happens. I've just lost control of the server. Hate it when that happens. So plan B. Looks like I have plenty of burst capacity. It is locked up. Oh, it's still locked up. All right, plan B. Let's attempt to get a save. So what I will do now is it's almost time for lab. What I can do is I can show you where I was headed, and we will pick this up again in our next lesson meeting, and I will hand off control to Farang in a few seconds, assuming the HTML. Oh, I just stopped the server. There's no way I'm going to be able to see it. Oh, the other one's broken too, huh? Can you all even hear me, or have I lost complete network communication? Don't even know it. Okay, got a thumbs up.
Oh, we can hear you. That should be locked up because it's rebooting. Okay, Farang, I will hand off control to you. That was not anticipated, but I guess that happens from time to time. And once it's back running again, I will, where are you? There you are.
So if you guys need a break, we are going to begin at 11:35. But please bring back your brains with you when you come back from the break. I'm going to need that.
Yeah, and short-term, medium-term memory. Don't go flushing that stuff down the toilet.
Yeah, you got me all jealous answering Dr. Cleveland's question at the beginning of the class.
Yeah, but they only did it for a minute or two, and then they went back to normal behavior. So I should have, so they won't be able to access the server for a few minutes. So when you start, go slow until I have this thing restarted.
Sure.
Oh, this is my favorite lab of yours. Because they get the true meaning of theology.
In the chat box, Travis says that the mayor heard you. That's why that's why the thing broke. Okay, so now we do the restart. Okay, the server should be running again.
Awesome, thank you. No, John, I haven't read that. Interesting title, by the way. What do you mean, Wally? No, never heard about it. Berserk the manga. Sounds interesting. I have to give it a try. Thanks for the recommendation. And Abby, how can you even call that the spring break? That was like a long weekend.
I just shut off my brain and just watched anime the whole like break.
Good for you, so it wasn't that bad.
Well, no, I received bad news, but you know, you just have to move on from it.
No, sorry. Really, Sean? I thought that you were going to have a great time. How can Vegas be meh? Ever? No, Edgar, I haven't noticed the break for at least 2 years now. Okay, so let me catch up with the chat. Ian, how can you say that about Vegas? It's one of the most unique civilizations in the entire world. Oh, I know. Okay.
Vegas was fine. Good food.
Yeah, the thing that I really find interesting about Vegas is that the things that most people try to hide about themselves in almost every other place on earth is not hidden in Vegas anymore. And they're out there, they're doing what they want to do without really bothering others, at least in my experience. And I kind of found that peaceful. Yes, that is also correct. So Wally, I wouldn't describe a master in computer science as extremely difficult. I think if you are interested and if you put a little hard work into it, you will ace it. So 11:36, let us begin the lab. We are going to talk about confidence intervals and A/B testing in today's lab and on Thursday's lab. So unfortunately for both ends, I need you to remember what we talk about today for Thursday as well. So do whatever you need to do, but try to understand what we discuss. Lab 16, Game of Gods and Men. So when I was putting this here, I didn't know that Abby is going to be in our class this semester, but now we have two people who are very excited about the statistics. Now, the example that we're going to base our first discussion on is about Italy and soccer. So first, let me ask for the first vote of the day. When you say football, what comes to your mind? Which sport?
American football.
Probably American football.
Depends where I'm at.
Yeah, it depends where I'm at.
The Cowboys.
So interestingly enough, most people in the world call the sport football, which is played with your foot and with a ball. The American football is quite different. But because we are dealing with a majority of American students, and I don't want to mess your brains over this, we are going to stick with the word soccer. So, the question is, how many people in Italy love soccer? So, if at this point you want to give me a guess, what percentage of the population you think love football in Italy?
I would say 45.6%.
Okay, that was pretty accurate. Any other guesses?
60.
I'm getting 30 from Jalissa, 60. I'm getting at least 75, 100%. Yeah, my own guess would be a very high number because football is a big deal. Soccer is a big deal in the Italian culture. So, I gave you a map to support the argument on soccer and football, so you can look at it and see how many people in the world actually call it soccer. So it's just Americans, Australians, and parts of South Africa. And in the rest of the world, it's mostly football.
I didn't know
Isn't it-
Australia. That's interesting.
Come again?
You can go.
I didn't.
Oh, I was going to say, I think maybe it's because football from the European side is more widespread. And I would say like
Exactly.
currently right now, the heart of football, like soccer basically,
Mhm.
you know what I mean? The heart of that is in Europe. And so
Exactly.
because of that, most people would take that as, you know what I'm saying?
Yeah, and the game is a British invention, so they came up with the name. But let us move on. We are going to talk about this question from two different perspectives or in two different modes, the God mode and the man mode. So, are you ready to play God?
Absolutely.
Okay, let's do it. In God mode, we are assuming that we know everything about our population. For the case of this example, it means that we know everything about the population of Italy. Okay? Now, suppose that we know, theoretically, the exact percentage of people in Italy that love soccer, and it's 75%. Okay? Let's create that. We are going to create 60 million, a population of 60 million people. And we know that 75% of them like soccer. So by running these two lines, I'll have the population of Italian people who love soccer and the population of Italian people who do not love soccer. 75% of the population, 25% of the population. Fair? Clear?
As water.
Okay, awesome.
As much.
Wait, what?
Was that a question?
No, he said mud. I got confused. Yeah, I'm sorry.
I didn't follow that, but it's all right. So let's create a NumPy array with 60 million elements with a 1 for each one person who loves soccer and a 0 otherwise. So what am I trying to create? An array. How many elements in that array?
60 million.
60 million.
60 million. How many ones in that array?
75%.
75% of it is going to be ones, indicating people who love soccer. And how many zeros?
25%.
25%. The rest of it will be zeros, indicating people who do not love soccer. So one may wonder, maybe this is how we got created in the first place. So we are creating this array with ones and zeros, and then we are putting them together. So this is the population of Italy. 60 million numbers, 75% of it ones, 25% of it zeros. Are we good? Okay. As a check, we can get the percentage of ones in the array by calculating the mean of it. And indeed, it is 75%. So you have 60 million numbers, 75% of them are ones, the others are zero. If I calculate the mean, I will get 75%. Is that clear? As water or as mud?
As water.
Better.
Okay, cool. Now, let's take a few samples and see what percentage do we get. So let's say that out of this population of 60 million people, I'm going to ask 1,000 people and see how many of them like soccer. What number do you expect to get?
750.
Come again?
So, sorry, 750?
Because
Because we're taking a sample of 1,000 people, and we're asking how many of them like soccer. And so if we're
Okay.
doing that, we would expect it to be 75% of 1,000.
Awesome. Yes, that is correct. Jalissa asked random people. Yes, my question was based on random people, but why do you care about them being random, Jalissa?
Well, because if it's like a country like Mexico, you'd be like, oh, okay, probably a majority of these people like. I was just asking if it was random because it's like it just depends. You know what I mean?
So at this point, since we are in God mode, you know everything about the population. So you know that the population that you're dealing with, Italy, 75% of people love football. Now the question is, if I go out there and I randomly pick 1,000 people out of the 60 million, what will be the percentage of the sample that love soccer?
75%.
So all of you are saying 75%.
It'll be close to 75%.
Okay, that's another answer. Close how?
Like,
Well,
Uh,
if you're picking 75% of a larger number, doesn't that mean that there's a pretty good chance that all the people in the 1,000 are all going to be soccer fans? Like the ratio might not scale down to 1,000. There's even a chance that none of them will like soccer, which is significantly smaller, but like it's a possibility that like it's not going to be directly 75%.
Exactly. And this is because of the nature of a sample. With a
It definitely-
sample, you cannot capture the entire population. We all knew that, right? Do you
Right, but
remember yeah, go ahead, Kate.
as long as you have more than like 100 samples, it's definitely going to scale majority of time though, right?
You can say that, but it really depends on the content or the sample size of each sample, and then how many samples you're taking. So in this example, let's say that we are going to pick 1,000 people from Milano with 2 or 3 of the most famous football clubs in the world. This will be one of my samples, 1,000 people from Milano. In the other case, I'm going to south of Italy to a fishing village, and I'm asking 1,000 people in there, and there is no football club in that village. Do you think that I will get the same percentage?
No.
Is that going to change my understanding about the population?
Yes.
Why?
Well, you just said there's no football fans in the fishing village, so that's gotta impact the population at that point.
You are still looking at the problem from a man's perspective, which is appreciated. You are trying to infer information about the population based on the samples. Currently, in the God mode, I already know my population completely.
It doesn't
So-
change. Oh, sorry.
Go ahead.
It doesn't change anything about the population because we already know what the population is. Just because we have a sample that tells us some people don't like soccer, we already know people don't like soccer.
Exactly. So let us pick a random sample and check the percentage that we get. 75%, 76%, 74%, 74%, 77%. So each time that I get a random sample, I'm getting a different percentage. What is similar between these?
They're all close to 75%.
They are all close to 75%, sometimes a little lower, sometimes a little higher, but they are all close to 75%, which is my population mean. Correct?
Yes.
Okay. Now, let us take 10 random samples and look at them. first take a look at this code block and tell me if there is anything confusing about it. I think you should have no problem with this, but let me know. All good? All clear? Water, mud, or honey?
Wait,
Clear.
why honey?
Well,
Honey's
honey
good.
is clear and it
Oh, acid.
magnifies things, so it's even better.
I can't read through honey, so I don't know about that.
Okay. So in my 10 samples, I'm getting 73%, 74, 74, 75, 78, 77, 77, 74, 77, 74. So pretty much the same thing that we observed earlier. We are getting numbers around 75%, but sometimes lower, sometimes higher. Okay? You can see that we're getting different values for each sample, but the intuition and the statistics theory says that the average of large amount of samples, this is pretty much what Caden said. The average of large amount of samples should be very close to the real percentage. What do we mean by the real percentage?
75%.
Yes, the population, yes. Let's do that. Let's make many samples and see what happens. So in this code block, I am creating, or I'm taking 10,000 samples with size of 1,000. So in each sample set, I am asking the opinion of 1,000 Italian people. And I'm calculating the percentage. What number did I get?
Rounded to 0.75.
Is it quite close to the population mean?
Yes.
So that was only to show you what this means. If we take large enough number of samples with a big enough sample size, we will get close to the true average, or to the true population statistic. Are we all good with that?
Yes.
Okay, so we created 10,000 samples, check the percentage of people who love soccer in each sample, and then just average them. We got 74.99, which is very close to the real value, 75%, that we, as the God, knew. But in the man mode, we didn't. So let's plot a histogram of all values we got in all the samples and look at the plot. What do you see?
Looks pretty normal.
It looks pretty normal. And I believe pun intended. So what does this tell you?
That's pretty vague.
Question. How can you relate? This highlighted a statement about mini samples and getting close to the population mean, and this histogram.
So then the larger the sample size, the more normal distributed it'll be.
Okay,
Something like that.
you're getting close,
Okay.
yes.
Is
Any
it
other
that-
ideas?
Is it that the bell curve shows the interval in the range of the distribution to find the mean?
So
The true mean?
let's say that the first sample I got gave me an average of 74%. I would be in this point on this histogram, correct?
Yes.
The next sample would give me a 76. I would be at this point of the histogram. The more samples I get, the higher frequency I will see in these numbers. And the numbers that get a bigger frequency, that are more frequent, will guide me to narrow down my understanding of the population's statistic. So this histogram is created by looking at 10,000 averages. And in these 10,000, you see that we are having a higher frequency around 75% here in the middle. That is how I am getting closer to the population mean. Okay? You look a little confused from the cameras that I'm seeing. If you have a question, ask.
I'm just having a problem with Seaborn.
Is it giving you an error?
Yeah, I don't really know what it is. It says this plot is a no. It says please adapt your code to use either displot or hisplot.
Are you using dist plot?
Yes. And like when I loaded up the lab, it was in raw. It wasn't even in code.
Yeah, it should be dist plot. Anyways, let me know if you managed to solve it. Okay, so we are going to do this process for an even bigger number of samples. Don't do it on your computers because this is going to take a while. I am going to take 1 million samples this time. Each sample is going to have 1,000 people in it. So I'm going to create a histogram based on 1 million numbers, 1 million percentages. And that will be how it looks. Based on this, if you wanted to pass a judgment about the population, what would you say?
That the mean is 75%.
What else?
Also that I suppose the range of correctness we have is from 0.68 to 0.82.
You're getting very close, yes. So looking at the center of the distribution is one piece of information. We've already talked about it, and you also mentioned it. Well done. What else can I see? What else can I infer from looking at this plot? Abby, go on.
Oh, I was seeing that there was higher frequencies for like around 74 and 76. I don't know what that.
Okay, so I can say that half of the samples are larger than 75%, half of them are less than 75%. That's another piece of information. We can say that roughly 25% of our observations are larger than 76%. I'm talking about this portion. Okay? We can also say that almost 95% of the samples are between 72 and 78. You see, if I go from 72 to 78, I'm capturing the majority of observations, which is calculated to be 95%.
So this basically allows us to not only look at the population, but also of the samples we took.
This allows us to infer information about the population on the basis of what we have seen in our samples. So do you remember over the past few sessions, we have been trying to move from samples to population? This is on the same lines. Okay. Now, if I get a box plot of this, what can you see in the box plot?
You can see the IQR, the medium. You can see.
Okay, what can you tell me about the IQR?
The IQR is from 0.72 to like 0.76.
0.72 is here. I think you mean
Oh,
0.74.
0.74. Yeah,
Yes.
and 0.76.
So
you can
looking
also
at that, what can you tell me?
You can tell. I can tell you that the medium is in 0.75.
Yes, but that's another thing. That is correct. So when you tell me that the median is at 0.75, you're telling me that 50% of the observations are above 0.75 and 50% of the observations
Yeah,
are
below.
below 0.75.
Yes.
Okay, let's deal on that. Put that aside. You told me something about the IQR. What is IQR?
IQR is the
Quantile range.
Yeah, interquantile range.
What amount of data can I capture within my IQR?
50%.
50%, because it's a difference between 75% and 25%.
Mm-hmm.
So can I say that 50% of my data are between 77.4 and 76?
Yes.
Awesome. Now, what can you tell me about these whiskers, the difference between these whiskers?
The two hold each one hold 25% of the other data.
25%?
Yeah, each. So the first whisker would hold 25%, and the second one would hold 25%.
So if I'm not mistaken, this is at 5%, this is at 95%.
Oh, they hold everything that's within, I believe, 3 standard deviations away from the medium.
Yes,
and then everything else
correct.
is outlier.
So we can also look at these numbers and pass a judgment about the amount of information that we can capture in that part, correct? Okay.
Yes.
Now, up to this point in today's lab, we have used a lot of samples. And we concluded that if we have a lot of samples, we are able to get close to the true values of the population. Now, at this point, many people might ask two important questions. How can I take infinite number of samples? And how does it help me? The answer to the first one is that if you are God, there's no stopping you. If you are not God, you can't take infinite number of samples. To answer the second question, let's go back to our example. So we initially took one sample of 1,000 people and got a value close to 75%. Do you remember this? Please say yes.
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 Okay. But it wasn't exactly 75%. It was a little lower or a little higher. For example, we got 74.3. We got 75.6, something like that. We wanted to know what is the chance that a random sample of 1,000 people will have 73% soccer lovers. Using the information above, we can say that there is a chance of roughly 20% that we will get a value that is smaller or equal to 73%. So let me highlight this. Read this statement. There is a chance of roughly 20% that we will get a value that is smaller or equal to 73%. Look at this plot and tell me how I am making that assessment. Any volunteers?
Does that have to do with the standard deviation?
No, only look at this box plot for now and tell me if you see a connection between data statement and this plot.
Is it because it's part of Q1 and it takes up like...
Where is your Q1?
Q1 is from 74 to 72. 71.
Your Q1 is going to be one number, and in this case, it is almost 0.74. Okay. So let's only focus on this. Let's only focus on 0.74. What amount of your samples are less than 0.74?
25.
25%. Why? Because that is our Q1. That is the beginning of our box. What can you tell me about the amount of observations that are greater than 0.74? Basically this part.
They're 75%.
75%. So looking at that specific number, and in this plot, you can say 25% of my data are less than 0.74, and 75% of it are greater than 0.74. What can you tell me about 0.75?
The median.
What amount of observations are less than 0.75?
50.
50%. What amount is greater than 0.75?
50.
Okay. Now, let's look at 0.77. What amount of observations are greater than 0.77?
20.
Almost 20. What amount of information are less than 0.77?
Below 0.77, 80.
Yes, 20 above, 80 below. Yes, thank you. So let's go and look at 0.73. What amount of observations are above 0.73?
Oh, 0.73, 20 as well.
80,
I mean.
80, yes. What amount are less than 0.73?
20.
Okay. There is a chance of roughly 20% that we will get a value that is smaller or equal to 73%. Can you relate this to the highlighted statement now?
You could say that based on the box plot, that 20% of the data is below or equal to 73%.
Yes. And this box plot is communicating the same histogram with you. It's just a different way of showing it. So we don't actually need to do the infinite samples. In other words, you don't have to be God. It would be cool if you can, but you don't have to. You will know why and how in a few moments. So with all due respect, let me take you back to the man mode. In the mad mode, in our horrid and miserable man mode, we don't know the actual percentage of soccer lovers in Italy. In fact, we know nothing about the population. So we do know one thing though. We just took a sample, and in that sample, we had 73% of people loving football. Okay? That is the only thing you know. I come to you, I come to your office, and I tell you I asked 1,000 people randomly chosen from the Italian population, and I asked them whether you love football or you don't. 73% of them, 730 people in that sample, told me, yes, we do love soccer. The rest of them said no. How can you use this information to understand or pass a judgment about the population? That's what we're going to learn. What we also do know is that if we took infinite number of samples, the distribution of their means will look like this. Do you remember this from the God mode? What kind of distribution is this?
A normal curve.
A normal curve, a normal distribution, or bell curve. Where is the center of a normal distribution?
At the 50th percentile.
Correct. At its mean, which for a normal distribution is equal to the median. Okay? Now, if I go one step to the right and one step to the left, and my step size is being equal to my standard deviation, I will be able to capture almost 68% of my data. Yes?
Yes.
If I go 2 steps to the right and 2 steps to the left from my mean, and my step size is equal to my standard deviation, I will be able to capture how much? 34 plus 34 plus 30, 13.5 plus 13.5. So this figure is calculated based on a normal distribution as you are moving towards the tails from your mean. Okay, so here mu is the population mean, real percentage of soccer lovers in our example, which in the man mode we don't know. And sigma is the standard deviation of the population again. So mu and sigma are population characteristics. If we know this, and we know the standard deviation, we are able to say that 68% of the samples will fall in the red area here, or more than 95% of the samples will fall outside the green area in the middle of this plot here. This is where the concept of margin of error becomes of great importance. Now, what is margin of error, or MOE? We calculate margin of error as this: Z multiplied by sigma divided by the square root of n. What is n?
Sample size.
Size.
Sample size. How many samples you have in the set. What is sigma?
Standard deviation.
Standard deviation. And what is z?
That your z-score.
That is the z-score. Yes. Now, have a look at this. Do you remember alpha from hypothesis testing?
Yeah.
What was alpha?
The
Very-
significant split.
So, Caden, give me your answer.
It's the barrier at which we set our rejection of the null hypothesis.
And it had a name.
Yeah, I don't remember the name.
Okay, Abby?
Was it the significance level?
Significance level, yes. Both Caden and Abby are correct. So, alpha was our significance level. We used to use it to decide the result of a hypothesis test based on comparing it with our calculated p-value. If you look at this two figures, it is basically telling you that with a smaller alpha, you're going to have a larger margin of error. And with a larger alpha, you're going to have a smaller margin of error. So if you want to be more confident about a test, would you rather use a smaller alpha or a larger alpha?
I would say larger, maybe. I don't know.
So I have one answer for larger. I have no answer from the rest of you. Come on, vote something in the chat box. If you want to be more confident about the results of a test, about a statistical interpretation, would you feel more safe? Would you feel more confident with a smaller alpha or a higher alpha? We have already answered this question before. So I have one answer from the brave Brandon, and the rest of you are all saying larger. Okay, Sean, Marlene, Celia also joined the club.
Wait, I have a question.
Come.
What is the null hypothesis here for it?
Doesn't matter.
Oh.
Under what circumstances would you reject a null hypothesis?
If the alpha is lower than 0.05?
If your p-value is less than 0.05, and 0.05 is your significance level. Sometimes you set your significance level equal to 0.05. Okay?
Mm-hmm.
So let's say that you get a p-value of 0.04 and your significance level was 0.05. Are you going to reject the null?
No.
Why?
I thought don't you reject the null if you have it over 0.05?
Yeah, if you have it below 0.05, you're going to reject the null.
Mm-hmm.
So 0.04 is the p-value that you have. 0.05 is your significance level. Are you going to reject or not?
Yes, you're going to reject.
Yes. Okay. So do you feel comfortable if your p-value is 0.04 or if it was 0.01?
4.
Why?
Wait, because you said 0.001.
Yes. So the threshold that you're comparing against is 0.05.
Yes.
Would you rather be very close to it or way below it?
Close to it.
No, that is the point.
I feel like I'm getting confused here.
Yeah, I understand.
My bad.
So do you remember the example? Who was I asking to shoot people with red bags? I was having an example with you that I asked that lady to shoot people if they have a red bag and to give them $10 if they have a blue bag. Please tell me that you remember the story. Okay, whatever. Wally, I was talking to you, right?
Yes.
Okay. Let's say that I ask you to sit in a room. I give you a bunch of bills. I give you a bunch of cash, and I give you a loaded gun. Okay? I ask you to look at the people who enter the room. If they are carrying a blue bag, shoot them. If they are carrying a red bag, give them cash. Do you understand the rules?
Mm-hmm.
Okay. The first guy walks in. He's carrying a red bag. What would you do?
Red bag, you give him money.
Okay. The second guy walks in, you give him. The second guy walks in and he is carrying a blue bag. What would you do?
You shoot him.
Okay. The third guy walks in. He's carrying an orange bag. What would you do?
You wouldn't give him money. Actually, you would give him less money.
That was a creative solution, but you don't get to pick. So
okay.
You have only 2 actions to choose from. Would you feel more comfortable shooting him because you feel his bag is closer to blue, or would you feel more comfortable giving him money because his bag's color is closer to red?
More comfortable giving him money since it's closer to red.
Because orange is closer to red.
Yeah.
Okay. The fourth guy walks in. He is carrying a purple bag. What would you do?
I'm gonna assume there's equal blue and equal red.
Mm-hmm.
So then I guess you can't do anything.
You have to pick.
Oh, then I guess shoot.
Okay. Now that you've made 4 calls in this story, I'm going to ask you which call was the easiest for you.
The orange one was easier. Well, the red one was easier.
The
Yeah,
first one and the second one were easy, and the third one and the fourth one was quite hard, right?
Yeah.
They were hard because you were getting close to the threshold of distinguishing red and blue. If you're far from that threshold, if you can clearly say this is red and this is blue, you have no difficulty in making the call. Am I right?
Mm-hmm.
Okay. The same thing happens for hypothesis testing. The distinguisher is your significance level. Let's say 0.05. You feel comfortable if your p-value is way below it or way above it. You can make a call when your p-value is close to that, but you wouldn't feel very comfortable about it.
Because you'd be like confused. Let's say like you made a mistake.
Exactly,
really
because that will be like making a call about the guy with the purple bag.
Mm-hmm.
Because it is very close to being red and it's very close to being blue, so it's not as confident.
That makes sense.
Okay. So let me see the chat box. Always safer to shoot from personal experience. I'm going to pretend that I don't believe that, Kaden. And Daniel said, hand him cash, then shoot him in the back. Too much Tarantino. Shoot him just to be safe. Okay. Now, we are going to mix what we understood from the God mode and what we understood from the mad mode. We are going to do mad mode. So, of course, the distance to the right and to the left is symmetrical. So if the sample percentage will fall 95% of the time between real percentage -3 and real percentage +3, then the real percentage will be 95% of the times between sample percentage -3 and sample percentage +3. This is a very confusing sentence. Read it 3 times, and then I'm going to ask you a question. Have you read it? 3 times?
Yeah.
Okay, awesome. First, let me see. Do you have any questions about it? If you read this and you do not have a question about it, I would have serious doubts about what's happening in this room.
Whoa. Okay. So this is my question.
Mm-hmm.
So it says if the sample percentage would fall 95% of the time between the real percentage. So are we assuming the sample percentage and the real percentage are the same thing?
No, exactly the opposite. We are trying to distinguish them. So in the God mode, when you knew the real percentage, the population percentage, we looked at a lot of different samples and we said, okay, in the majority of cases, in the 95% of cases, we are somewhere around this population mean -3 + 3. Okay? That was what we understood in the God mode. Give me an okay and I will move on.
Okay.
Okay.
All right.
Question? Okay. Now, in the man mode, we are saying that the real percentage is going to be around samples percentage 95% of the times. So in God mode, you know population percentage. In man mode, you know sample percentage. Are we good?
Yeah.
In the man mode, you're going to say, okay, 95% of the times, the true population will have a percentage or a mean equal to my samples percentage minus 3, my sample percentage plus 3. So you're using your sample to pass a judgment about the population. You're giving a range for the possible population mean to fall into based on your sample. Did you understand it?
No.
Okay. In the example that we're discussing, you went to Italy, you came back to me and you said, I asked 1,000 Italian people whether they love soccer or not. And 73% of them said that they love football. Okay? I ask you, so you asked 1,000 people, we know that 60 million people live in Italy. What can you tell me about the population based on your sample? You're going to come out and say, based on what we discussed today, the real percentage of Italian people who love soccer is going to be somewhere between my samples mean, which is 73%, plus 3 and minus 3. So you know that somewhere around 70 to 76% of Italian people love soccer. That's the information you can give me about the population based on what you had on your sample.
That makes sense. Thank you.
It does?
Yeah.
Do you feel good about it now?
Yeah. So basically what you're saying is that if 95% of the sample fall, or the sample percentage falls within the real percentage, it's more likely that if you're looking for a sample percentage, it will be in the, you can use one to find the other, basically.
Exactly. Yes. And since we are men and we are stuck in the men mode, that's usually the most common approach for us. So we have samples and we want to go from samples to populations. So based on what we see in our samples, we can pass a judgment about the population. Okay? Do you have any other questions about this? Okay. So if we took a sample and got 73%, we can say that we are 95% confident that the real percentage is between 70% and 76%. This is the confidence interval. The interval is 73 plus or minus 3, and the confidence is 95%. Now, as another example, from a normally distributed population, we randomly took a sample of 500 students with a mean score of 461 on the math section of SATs. Suppose the standard deviation of the population is 100. What is the estimated true population mean for the 95% confidence interval? The information that we have, is it about sample or is it about population?
It's about population.
Is it?
So we're using our sample to infer the population mean.
Exactly, because we don't know the population. So from a population, we randomly took a sample. After this moment, everything we know is about that sample because we are in the normal man mode. So step one, let's set up the parameters a sample size of 500, a sample mean of 461, confidence level 95%, standard deviation 100, z is equal to 1.96. What is that?
The z-score.
Where did I get that?
From the Z table.
There is a table out there that you can easily Google and find if you hate books. And you can use that table to get the Z value associated with different confidence intervals that you want. So for 95%, that is 1.96. Now, I'm going to import math. I'm going to calculate my margin. How am I calculating my margin?
Using the formula given above.
Yes. So I'm multiplying my z-score by my standard deviation, and I'm dividing that by the square root of my sample size. And my margin of error is equal to 8.76. In the next step, I'm going to say x bar, which is my sample mean, minus the margin of error, give me the lower threshold. And x bar plus margin will give me the upper threshold. And I'm going to come out and say the true population mean will be captured within the confidence interval of 452.2 and 469.8, and the confidence is 95%. Clear?
Yeah.
Awesome. 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 I'm happy. Now, if you want to read a little more on confidence intervals, here are 4 interesting reads and 3 videos that you may find helpful. Now, I'm going to take the risk and ask for your short-term memories. What do you remember from the lecture Dr. Cleveland gave you less than an hour ago about A/B testing?
He told us that you would cover that.
I was there. So anything that you remember, what is A/B testing? What are we trying to achieve?
A/B testing, he said, was basically the tests that we did last class, but basically put together.
Okay. What else did he say?
We
Isn't it like if our data sets came from the same or different distributions or something like that?
Mm-hmm. Yes. So let's have a look at this example, and I hope it helps you better understand what A/B testing is. Imagine you're in charge of a website, God forbid, an online video game shop or something. You have the current version of the website, which we are going to call A, but you aren't happy with it. So you have been working with this website for a year, and you kind of feel that you're losing customers because of the design of the website. So people come in, it looks boring, it's slow, it's hard to read, something like that. For instance, you're not selling as much as you like. You want to change the design of the add to cart button. So previously, this was your design. Now this is going to be your design. We are going to call this B. And you are interested to see whether by changing this, you are going to increase your sales or not. Here's what we will do. You set up your website so that half of the people are directed to the old website with this design, A, and the other half will go to the new design, B. You will gather data on both groups, and you want to know with confidence, does the change I made increase the sales? So before we move on, the group that goes to the old design, 10% of them make a purchase. The group that you send to the other design, 90% make purchase. What does that tell you?
That they like the button B.
That button B is good, and people are weird that something this easy is impacting them, but you don't care, you want to make money. So This scenario is a typical A/B testing. So this is an A/B test. Often this is used interchangeably with the term split testing, though in general, A/B tests test for small changes, and a split testing might be when you present two entirely different websites to the user. So these are tiny differences. You don't have to worry about them. Two questions. Why not just change the website and monitor it for a week?
Because you can
Because
lose
you're
money.
because you don't know what, say, it has a horrible effect, and you can lose money. So even though you're going to take a cut, let's say by splitting your people on, like, customers into two, at least you'll still be making some form of money.
Yes, and also you want to be fair in your analysis. So let's say that I give my old design a week and I give my new design a week, but the second week is close to Black Friday or some other occasions, and more people are going to come on that week. That is something that you are not controlling for, so your comparison is not going to be fair. You want to try and make the two scenarios very, very identical, with the parameter that you're looking for being the only change. So I want my group A and group B have the exact same experience. The only difference will be the design of the add to cart button. So
basically, you kept a controlled variable, so you can see the changes in different.
Yes, exactly. So another question, why is it not an ABC test? Shall I only look at two alternatives? Can I have three designs? Yes, you can. You can have as many alternatives as you want, but first of all, they wanted to keep the name quite easy and simple. And also, when you increase the number of alternatives, it will be hard to maintain the fairness of the test. It will be more difficult to draw statistically significant conclusions. This one is specifically for Caden. So let us assume you have 1,000 users. 550 were directed to site A. 450 were directed to site B. In site A, 48 users made a purchase. In site B, 56 users made a purchase. The question is this a statistically significant result? Are we happy with the change? Are we going to change the logo or not? So numbers in group A, 550, numbers in group B, 450. How many clicks, how many purchases? 48 for A, 56 for B. And I'm going to calculate rate A and rate B. And let me actually go on Prentice. So we have a rate of 9% for group A and 12% for group B. Judging these two numbers, are you happy with the change? Are you going to keep the change?
No, it's not really that big of a difference to me.
Okay, so you would rather stick with your previous design?
Yes.
Okay.
It's only 8 more users that are clicking the, cart button.
But
Okay,
wouldn't those 8 more users like still bring in more money? You know what I'm saying?
So an increase of 3% is good enough for you?
Yeah, any increase is good. Because
Okay,
over time, that 3%, depending on how much you're selling, is a lot of money.
So Jordan has said no. Wally said yes. Jalissa is keeping the change. Harper is keeping the change. Aaron is keeping it. Do I have anyone who wants to join Jordan's team? The conservative website manager? Dude, you're alone. Let's see if you were right or not. So you can click a button or not. 2 discrete options are available. So this is a textbook binomial distribution with some unknown rate for site A and site B. We don't know the true click rate, but we can estimate it using our sample. I am bringing these in, you know these two. I'm also importing the binom function from Scipio-Stats, and this is for binomial distribution. I am defining my clicks. I am getting the probability for A and probability for B based on the numbers that I had in each sample set, numbers and rates. And I'm going to make the bar plot based on the clicks and the probabilities. So I'm getting this, A and B. A is the old design, B is the new design. Look at this plot and tell me if you want to switch teams. Do I have anyone who wants to join Jordan's team, or if Jordan wants to change his team? Do you think these are different enough?
Yes.
Kind of. I would say they're slightly different, but not a big difference for me to change my answer.
So you're still staying. Okay. So we can see here that B has an edge, but it's certainly possible if we pick two random points according to the histograms for A and B, that A might actually be higher than B. Okay? So especially in this area where we are having the overlap, there are points that A is higher than B. As we are interested in the average number of cells, this averaging of an underlying distribution means our final estimate will be well approximated by a normal distribution. So let's reformulate using the normal approximation here. I'm going back to the norm function, and I'm calculating the standard deviation. You can actually go and check what is happening in this code in the Wikipedia page, but I will end up with these two. So I converted the binomial distributions to normal distributions here. Now I have A and I have B. So looking at this plot, would you like to change or would you like to stay?
So is it basically now a question of the orange gets more purchases, but less amounts of it, or what?
So when you look at this, let's say I pick this point. Which model, A or B, is giving me a better purchase rate?
Orange.
Really? I think both of them are giving me the same thing at this point.
Yeah,
Oh,
I
yeah.
was gonna say because they're meeting at a point.
So, but if I move a little to the right and I come here, which model is better?
Orange.
B has almost 20% chance of giving me a purchase rate, but A is close to 0, maybe 1 or 2, right? So from this point to the right, B is winning. From this point to the left, who's winning?
A.
A is winning. So this is what you can infer from the plot. The decision that you're going to make completely depends on you. I have Jordan, who is very happy to stay with his old design, and I have the rest of you who were very happy to go for the B. Jalissa is changing, and she's saying that I feel they're the same. So Jalissa, are you staying with your old design?
I don't know. I'm kind of indecisive right now. I really don't know. I'll probably stick with the change.
Okay, so it's still Jordan standing alone on his grounds.
I have
Let's
a
move
question.
on. Go ahead.
What does purchase rate mean here?
purchase rate is out of, for example, 1,000 people or 100 people, how many of them are going to make a purchase?
And so probability is the chances of them making a purchase.
Jordan, are
So-
you angry at me or you're just excited about your winning?
No, I'm just saying that I think A has got such a higher probability of people pressing that button. That's all
It
I'm like.
has a higher probability for a
Equal.
purchase rate of, for example, 0.08. But what about for a purchase rate of 0.14? See? It's not such an easy call. I respect your decision and I want you to stay with it if you like. But it's not an easy call. It really depends on which part of it you want to highlight for yourself. So this is also a better plot than the first one because we've removed the confusing effect of site A and site B having a slightly different number of visitors. So our question is still the same. What is the chance that a draw from B is higher than a draw from A? And or is it significant? To answer this, let us utilize the handy fact that the sum or difference of normally distributed random numbers is also normal. So if I have two normal distributions, if I add them or if I subtract them, the result is still going to be a normal distribution. We know that. This is simple. Take the difference in the means and sum the variances. We'll do two things below. First, get the z-score, and second, plot the proper distribution. So I'm calculating the z-score, and I am calculating p, and I am going to plot this. So now, instead of 2, I have 1 plot. And this is difference in purchase rate. So I have subtracted the purchase rate from A and B. What do you see here at 0? What does 0 mean?
0 probability, or no, we're looking
No,
at the bottom,
your
right?
probability is on the y-axis. This 0 is on the x-axis, which is showing you the difference in purchase rate. So when that's 0, it means that there is no difference in purchase rate. Okay? Anything after this is showing that B is winning. Anything before this means that A is winning. Which area you think is bigger, the right or the left?
Right.
Definitely the right.
The right.
Okay. See, he at least has the courage to go with the science. That's good. So we can say that given the null hypothesis that B is less than or equal to A, this was basically Jordan. We would expect to get this result or a result more extreme only 2.9% of the time. Where am I getting this 2.9? This is the area of this
In the white
left.
region.
Yes, white region, exactly. As that is a significant result, typically a p less than 5%, the significance level will be significant. We reject the null hypothesis and state that we have evidence that B is greater than A. Okay, so basically, we ran a hypothesis test to see whether B and A are different or not. If the calculated probability, if the calculated p-value was greater than 5%, we would say B is equal or less than A. So we would stay with A. But since our calculated p-value is less than the significance level, it is less than 5%, we are going to reject the null and we are going to say, no, B is in fact better. Let's change the design. So we've made a lot of plots for this to try and explain the concepts. You can easily write a tiny function to simplify all of this. Whether you want the confidence or the p-value just means changing the final norm CDF to norm SF. So this is the function that we are writing, get confidence A/B test. We need number of clicks for group A, how many customers we had in group A, number of clicks in group B, and how many customers we had in group B. We are going to calculate the rate, we are calculating the standard deviation, we are calculating the z-score, and we are getting the result that we want. Oops, name norm is not defined. Yes, that's my bad. So what is this number?
Is that the slight increase B has over A?
That is the p-value that we calculated up here. Okay, so if your p-value is small enough, you can reject the null hypothesis and decide that B is a good alternative to go with. Okay, so if you have a problem like this, you don't have to make all these plots. That was only for us to explain a few things. And remember non-parametric statistical hypothesis tests that we discussed last week? We can use them here. So imagine we have the raw results of clicks, purchases, as zeros and ones in our distribution. I can actually run a Mann-Whitney U-test for null hypothesis that B is less than or equal A and get a p-value of 0.28, which is very close to the one that we calculated up here. Since this is small enough, we are rejecting the null and we are saying that no, B is greater than A. That's another way of doing that. So A/B test is a quite simple extension for hypothesis testing. It just has to have a different name because people in business use this a lot and many of them suck at statistics. So any questions about A/B testing? Any questions about why we decided to change the design of the add to cart bottom?
No.
Not any at the moment, no.
Okay, Jordan, are you changing your design now?
Yeah.
There you go. Otherwise, you're going to be inhaled by Amazon. So some great reads on A/B testing, some videos that you can watch. And as an example, I've asked samples, populations, men and gods, why are confidence intervals useful? Okay, so that's what I had for today. Thank you very much for listening to me. Thank you very much for answering the questions and playing the games. I am going to pass the host back to Dr. Cleveland. Dr. Cleveland, are you there?
Okay, welcome back to me. And everybody have a...
I think your camera is off also. There we go.
There, have my black hat on.
Yeah, the Heisenberg hat.
There's a annual conference in Las Vegas called Black Hat. And you can get hats just like this there. It's a very expensive conference to attend because it's for computer hackers. Legitimate corporate ones whose job is to protect computer system.
Yeah, Harper belongs to the committee there.
Oh, very cool. Anyway, everybody have a great afternoon. We will resume interval estimates on Thursday. I got all my script started working again. So part of why it does that is it's actually one of those cells takes 8 minutes to complete. But it draws some really cool pictures, which we will pick up with on Thursday. In the meantime, work on the lab, work on your pending homework assignments. We will schedule a review session sometime this weekend for the next upcoming exam. By way of warning you about the exams everybody is worried about, it will be on hypothesis testing, interval estimates, descriptive statistics, and what else have we done since the last one? I think that's it. So good luck and have a great afternoon. Bye-bye.
Take care. Be safe.